Hi, this strange looking diagram is a representation of the Earth's magnetic field. It looks complicated, but we're going to look at a slightly simpler version. This video, though, is really focused on why we have a magnetic field in the first place. Without it, we perhaps might end up like Mars. It does help protect our atmosphere. But the origin of this field is an interesting one, and it's something that we as geologists need to understand. Okay, this is a more conventional view of the magnetic field. We can see that the arrangement of this field is very much like that of a bar magnet. It has the same field arrangement, the same idea of polarity of a north and a south magnetic poles, and the arrangement of the field, what we call it, is polarity, as in fact magnetism flows from the south to the north. Now we're familiar with this view, but it's actually quite unusual. It's a bit weird. The Earth can't be a bar magnet. We know that from the internal structure of the Earth. We know it has concentric layers. There's a bigger problem too. The Earth is simply too hot. Hot things are not magnetic. There's a property called the Curie temperature, or the Curie point, a temperature above which materials aren't magnetic, below which they can be. The Earth is way above the Curie temperature. So how can a body that's not magnetic be magnetic? To answer this, we need to look at the structure of the core, and particularly the outer core. We know from the movement of S waves that the outer core is liquid. We know as well from evidence from meteorites and also the density of the core that it's made of iron. But this is going to be at a temperature of several thousand degrees centigrade. So to understand the magnetism, we need to think about the outer core a bit like an electromagnet. We know that there must be convection currents happening within the outer core. So these convection currents are going to line up the iron particles within the outer core to create, I suppose, like coils of wire. With these coils of wire, we can get a small electric charge passing through, or passing around, should I say, these convection cells. Now, any electric current generates a magnetic field, but it's going to be way too small to generate what we see at the surface of the Earth in terms of the Earth's magnetism. The key to understanding this is to remember that the Earth is actually rotating. So if the Earth is rotating, we now have coils of wire rotating in a magnetic field. That generates more electricity. As it generates more electricity, it'll generate a bigger magnetic field. The result is the magnetic field that we can record at the Earth's surface. Now, the fact that the Earth is what we call a self-exciting dynamo, it's a bit like the dynamo that can generate electricity on a bike, perhaps. The fact that this magnetic field is generated as an electromagnet within a liquid outer core also helps us to explain other features. For example, the location of the magnetic pole changes over time, it drifts. Doesn't go that far from the geographic pole, but it does move. We know as well that the polarity of the field flips periodically, although we don't have a good model for why that happens. So, The result of this is our magnetic field. This magnetic field gives us a lot of information, a lot of evidence for plate tectonic movement. But more about that in another video. We can even see the reversals in magnetic polarity preserved in oceanic crust. Another key evidence for plate tectonics. So, to conclude, the Earth's magnetic field isn't a permanent one. It's an electromagnetic field generated by convection in the outer core. We do need to know where this field comes from. Perhaps even more importantly, we do need to be able to apply our understanding of this field to help us explain big geological ideas like plate tectonics. Don't forget to come up with your interesting question and bring it along to class. I'll see you then.